Okay, our new topic is the magnetic field on its axis. In the last video, we did the magnetic field at the center of a circular coil. Now here we have to do to find the magnetic field on its axis. Let's suppose before starting this topic, I give one example of the linear conductor. Suppose if the linear conductor here and it is passes the current, so it generates the magnetic field in a circular form. And the point P is here, so the distance denoted by the R. So what would be the direction of the magnetic field? If it is going up, so the magnetic field goes inside here and comes like this out, going inside and coming out. Okay, so if suppose I go to the top, so I cannot see the length of this wire. I can see only the tip of the wire. So the tip of the wire looks like this. And if I go at the top, so this line will move, I can see like this, and the point is here and they are. And if the dot is here, that means the current is coming out. If the current is coming out, so see, the direction of the magnetic field goes up. Okay, and this is called the horizontal X, this is called the horizontal Y. Initially, the direction of the magnetic field goes up and it has the direction as the Y axis has. Okay, let's suppose I fixed this point P. If I rotate this point, so it comes like this. It is a plane for the X axis, there is the Y axis. Earlier this line is here. Now if I rotate this point towards up and these two are the perpendicular, it means ये ऐसा है. If I fix in, तो ये इस तरह से shift होगा. So the magnetic field goes like this, and it is making the angle here. जितना यहाँ तक ये turn होगा, so the angular displacement called theta, and this theta and the angular displacement which is here always be same. So you can see if the current carrying element, which is a straight conductor, if we are imagining here, so the magnetic field goes like this. And this angle always be same. So I am giving only the this example to understand. Now move to the next. Let's suppose there is a circular coil. This is called the front portion, dotted line, the dark line, and the dotted line shows the back portion. There are 2 points. And this is called the axis. There is a point P where we have to find the magnetic field, goes towards the x-axis. Okay, and there is the y-axis. So I can show it like this. Okay, in this circular coil, the distance of center O to P, you can represent it by the small x, and the radius I can represent it by the small a. If I take the 2 element, one is called the P, another is called the Q, and if the current is going like this, going back comes to the front. So at this point you can imagine the current is coming like this as the thumb is going out from the board. Okay, if it is coming like this, the magnetic field goes like this, and the distance of P to P I have taken. Let's suppose this is the P dash. Okay, so P to P dash is R, and this is the right triangle here. Then this R is equal to under root A square plus X square. As I told you, if this is the R and the current carrying element is here, so the magnetic field definitely will move here. So this is called due to the small element dB1. And here is the angular displacement, you can write as the theta, and this theta and angle here which is here, theta always be same. We can do the same exercise from this point. If this is the distance from Q to P dash is the R, so the R has the same value under root A square plus X square. Okay, and again the magnetic field which is here, see the current is coming and going like this inside. Okay, so the magnetic field goes towards down. but it has one angle. So perpendicular direction where would be? It would be here. So again it would be dB2. Its component for the y-axis comes down, and the theta which is here always be equal. So these two theta all are same. In this diagram, this R and the radius, the magnitude of the current always be same. So you can say the value of dB1 and the dB2 are same. Here we will write here dB1 equal to dB2 in terms of magnitude. Okay, and R is equal to under root R square plus X. This is A square plus X square. Okay, we will find the value of dB1. Then value of dB1. The value of dB1, it is equal to mu 0 by 4 pi dot I dl sine 90 degree divided by the R square. Okay. Here the sine is the 90 degree due to the center on the element. So the dB1 equal to mu naught by 4 pi dot I dl by the value of R square would be A square plus X square. So here you will write A square plus X square. This is the equation number 1. Okay, this is the value of the dB1. Here the dB1 is going here, dB2 is going here. But what would be the resultant direction of the magnetic field? For it, see, the dB1 you can classify along the x and along the y-axis. Similarly, we can classify the dB2 along x and along y-axis. One more thing is, the dB1 was previously in y direction. So the y-axis will be its horizontal and x-axis will be its vertical direction. So for it, I have to write dB1 cos theta. I'll write it. And here you will write dB2 cos theta. That means the horizontal component of the dB2. These two directions are equal and opposite, so they will cancel to each other. And here, if this is horizontal for the dB1, so it becomes a vertical for dB1 and as well as for the dB2. So here you will write dB1 sine theta plus, because these two have the same direction, dB2 sine theta. So we will say the the component dB1 cos theta and dB2 cos theta cancels to each other. So the resultant magnetic field, then net magnetic field is called this is dB1 and the dB2 sine theta you can write as the dB equal to no need to write the dB1 plus sine theta and dB2 sine theta, because if you are taking the two element you will find the two equation. If you are adding more and more elements, so the number will increase. So better is then resultant magnetic field. Yeah, resultant magnetic field B is equal to summation of dB1 sine theta. Yes, that would be better. Okay. Next, the B is equal to summation dB1. This is the value of the dB1. Put it here. Mu naught 4 pi dot I dl by a square plus x square sine theta. And as we know, summation dl, that means overall circumference. So the b is equal to mu naught by 4 pi dot I dot 2 pi a, because the radius of the circular coil is the a, and a square plus x square dot. What about sine theta? See, there is the triangle. Triangle PO is this P dash. So the theta is equal to perpendicular upon hypotenuse. So it is the perpendicular A divided by hypotenuse is the R, has value under root a square plus x square. A square plus x square. Let's suppose the number of terms is the n. So I can write the n also. So the n I 2 pi a dot a. In the next step I can write mu 0 by 4 pi dot ni dot 2 pi a square divided by a square plus x square under root a square plus x square. So you can write easily a square plus x square whole power 3 by 2. This is the resultant formula due to a circular coil on its axis. Please note it down. Okay, coming next. B is equal to mu naught by 4 pi dot ni 2 pi a square upon a square plus x square 3 by 2, and where we know all the name of the variables. Let's suppose we are talking about some cases. Some case. Point number 1. If x is equal to 0, what it does mean? If x is equal to 0, that means your point P is on the center of the coil. So x is equal to 0, then what would be the formula? B is equal to mu naught by 4 pi dot ni 2 pi a square, and x is 0, then a square 3 by 2, then a cube will left only, and this cube square cancel, only one a is left. This is 2 pi, this is 4 pi, so you will make it cancel, the 2 will left. So what would be? The b is equal to mu naught by 4 pi dot, so not this is the 4 pi, is mu naught by ni to a. So this is the formula which we know. Case number 2, here x is equal to 0, let x is equal to infinite. If x is equal to infinite, that means the point P is very far off from the coil. So the magnetic field inversely, so that's why it becomes the 0. B is equal to 0. Point number 4, point number third is, if the x is equal to the radius a, then b is equal to, here, mu naught by 4 pi dot ni 2 pi a square divided by, here the x square, this is 2 a square and cube. Okay, so the 2 cancels, this pi will cancel, only the 4 will left. Okay, one we have to take the 2's also, so it would be 2 to the power 3 by 2. 2 to the power 3 by 2. Okay, yes, 2 to the power 3 by 2, and this 2 pi and this 4 pi will cancel, so this 2 will left, and this is a cube and a square cancel. B is equal to mu naught 2 dot 2 whole power 3 by 2 ni by a, and this is becomes 2 to the power 1 becomes 2 to the power 5 by 2. So ni 2 to the power 5 by 2 A. This is the formula. 2 is here only. Yes. And in the next case, case number 4, see here, very important. Let there is a circular coil. This is the center, has the radius A, and this is axis horizontally passes. This axis called the x-axis, and the particle is very far. Particle is x is equal to plus infinity. The particle can be at x is equal to minus infinity. As we know, when the point P is at the center, where the x is equal to 0, so the magnetic field becomes maximum. I can draw the graph here to make you understand. This is the point where x is equal to 0 on the graph. This is the point where x is equal to minus infinity. This is the point where x is equal to the plus infinity. At infinity, where it is positive and negative, doesn't matter, the magnetic field always be 0. So on this line, we can show the dot. And when this point P will comes closer towards the center, so the magnetic field increases, because the relation between the distance and the magnetic field is inversely proportional. So it increases like this. Let's suppose at the center the magnetic field increases. That means the point P reaches up to the center. And when it crosses this coil and moving towards the minus infinity, the magnetic field decreases inversely like this. And at x is equal to minus infinity, again it becomes the 0. So its magnetic field increases like this and decreases in this way. Here are 2 points you can denote. This called the point 1 and another point 2, where the magnetic field is similar. And the magnetic field will be similar at the distance where x value has a by 2. That means at the half of the radius. Okay. Note it down. Let's suppose there are 2 coils, coil A and coil B, having the same radius, having same magnitude of number of turns, having same flow of current. They lies on one axis, and let's suppose a point P is moving towards this direction. That means from positive infinity to the next infinity. And this is called the positive infinity. Then it comes from here and goes towards the negative infinity. So I have taken one line over here where I can show some dot. When it passes through this center called center C1, where the magnetic field would be the maximum. So at this point, at C1, its value becomes the 0, x is equal to 0, and the magnetic field becomes the maximum. Similarly, when it passes from the center C2, here its magnetic field becomes maximum if both have the same magnitude, so these 2 points will come on the same line. And here it is infinity, and I can show here the minus infinity. Okay, when it comes here, so the magnetic field increases in such a way, and when it goes from this C1 towards this, so it comes like this and decreases here. So this is the line shows me it is decreasing. Okay, and here when it reaches up to the center C2, so the magnetic field again increases. Okay, so at somewhere here, like, so these 2 points can cross here, and again the magnetic field at the C2 becomes maximum, and when it moves towards the minus infinity, the magnetic field decreases in this way. So at this point, the magnetic field increases, and the magnitude of the magnetic field can be same if the gap between these 2 coils is equal to the radius. So at here, But here the magnetic field becomes maximum. Please note it down.